kind of as a reminder, we were practicing applying what we learned about intermolecular forces to actual molecules. So let's just recap. Can anybody tell me or remind me of the types of intermolecular forces that we learned about?
Dipole, dipole.
Dipole, dipole. London, dispersion, and hydrogen bonding. Good. So those were the three, and we said hydrogen bonding is the strongest. We said London dispersion is the weakest. And we said to have dipole forces, you got to be a polar molecule. So we were reminding ourselves a lot about how to judge polarity, bond polarity, and when a molecule is polar. So it's kind of where we left off. Now I want you to look at this slide. We're going to do a little more practice to just drive a few more things home. This is really more so pertaining to hydrogen bonding. And the lab for next week is all about hydrogen bonding. So what we do on this slide, pay attention. It will tell you exactly how to do the lab for next week, pretty much. The only difference is we're going to be drawing this out, pen and paper, and the lab will use the tool on Mastering Chemistry, the one y'all all love, to draw molecules out. Okay, so this one says, which of these species below can form a hydrogen bond in its pure form? Okay, what does that mean? That means if I had one of these molecules and then next door I had an identical molecule, could they hydrogen bond together? Can it hydrogen bond with the same molecule of itself? Okay, and if it can't, then which one could hydrogen bond still, but with like a water molecule? So before we start really analyzing this, someone remind me, what were the two requirements that we had to meet to be able to hydrogen bond? We have to have at least one of the two, but there are two different ones.
Hydrogen has to be positive.
Okay, so we got to have a positively polarized hydrogen. Good. What was another requirement?
Janelle said it in the chat.
Oh, Janelle and Sarah said it in the chat. Yes, a lone pair on a nitrogen, fluorine, or an oxygen. So we've got those right there listed. Now, I want to review the slide we wrote out for just a second, because we said even if you have just one or the other of those requirements, you can still hydrogen bond, just not with yourself. So let's remember this first thing up here. Molecules that have both a donor and an acceptor. So hold on, which one do we call a donor? Which one do we call an acceptor? The positively polarized hydrogens we call donors. The lone pairs on an oxygen, nitrogen, fluorine we call acceptors. Okay, so if you have both a donor and an acceptor, you can hydrogen bond with an identical molecule just like that. But if you have either, so one or the other, a donor or an acceptor, not both, you can still hydrogen bond, say with a water molecule, just not with yourself. So if you have a donor, you can hydrogen bond with any molecule that can provide you an acceptor. If you have an acceptor, you can hydrogen bond with any molecule that can provide you a donor. Does that make sense? Okay. And then we drew an example of how. And this kind of stuff right here is what you're going to illustrate on the lab. If I say, here's your, draw the Lewis structure for this molecule and then show me how it would hydrogen bond with a water molecule, you're going to draw in a water molecule with the opposite portion, donor or acceptor, oriented towards your molecule where it would hydrogen bond. Okay. And I'll probably do a little intro video for the lab so you guys can know exactly what I'm looking for on that. So we're going to do this problem here, but we're only going to look at 3 of these for time's sake. We're going to do 1, we're going to do 2, and I'm going to call this one 3. We're going to do those 3. So let's look at this first one. We're asking the question, can it hydrogen bond with itself or with a water molecule? And remember why hydrogen bonding is so important. It affects like properties like the boiling point or the melting point, and it can raise those quite a bit because hydrogen bonding is a really strong intermolecular force. It takes a lot of energy to break apart those bonds and melt or vaporize substances. So we've got C2H6. This molecule only has carbon and hydrogen. So what do y'all think about that one? Y'all are about to make me yawn. Y'all know yawning is contagious. I'm seeing so many of y'all yawn. But I just had my espresso, so I think I'm good. What do y'all think about C2H6? Can it hydrogen bond? Sarah says no. Dakota says it's nonpolar. I agree. When you have a molecule that is only hydrogen and carbon, it is completely nonpolar, because here's the kinds of bonds you could have. You could have a carbon-carbon bond. You could have a carbon-hydrogen bond. I don't care how the molecule is arranged. If these are the only kinds of bonds in the molecule, it's nonpolar. So no, it cannot hydrogen bond with itself, with water, with anybody, okay? Molecule number 2. This is a condensed structure, CH3NH2. Take a second and draw it out. How do you think this looks? Put any lone pairs that need to be in there. So you should have your CH3 group like this. And then we have an NH2 group connected. And nitrogen always has a lone pair. All right, so what do y'all think about this molecule? Do we have any donors? Do we have any acceptors? Do we have both? It can H bond. We have acceptors. Bailey says both. Okay, so we know positively polarized hydrogens. Those are the ones that can be donors. And to be positively polarized, you have to be bonded to, where was our requirements? Right up there. Bonded to a nitrogen. And we do. We have 2 hydrogens in our structure that look like this. That's a polar bond. I realized I was doing a whole lot of this on Tuesday, but I was using this table. This was from chapter 4. Do y'all remember this table? This is literally the lecture from chapter 4. And this is the table. You'll have this on your resources page for exam 3 that tells you when a bond is polar or nonpolar or blah, blah, blah. So if we were to look at the electronegativity difference values between hydrogen and nitrogen, it would be between 0.5 and 1.9. So it is a polar bond. So the hydrogens connected to nitrogen, we will just show that they are positively polarized. And both of these, because of that, are donors. So we can hydrogen bond for sure with at least a water molecule, but do we have any acceptors? I'm seeing a lot of people, Ashlyn, they both say acceptors, people saying both, and that's true. This lone pair right here on the nitrogen, that is an acceptor. Because we have both donor and acceptor, we can H bond with itself. And it can also H bond with water. Any questions there? Okay. So let's go over to number 3 now. CH3O, CH3. This is another condensed structure. What do y'all think this looks like? Can't bond. Can't bond. Can't do it. Let's see. Should have a CH3 bond. All right, this is what you should have. Is that what you have? Is that what it looks like? Okay, first off, do we have any, if we're asking about hydrogen bonding, do we have any donors? Well, all these hydrogens are bonded to carbon. And remember over here, we said these bonds are never polar. So no donors, no hydrogens that are positively polarized. But what do we have?
Acceptors?
Yes, where? On oxygen.
Oxygen.
Yep, we've got two, one right here and one right here. These are acceptors. So it cannot hydrogen bond in pure form. Answer to that question is no, all right? But could it hydrogen bond with a water molecule? The answer to that is yes. How would that look? How would that look? Let's take a second and draw. I'm going to erase this so that we have some space to draw a little hydrogen bond. So I'll just say this one's also an acceptor. Let's draw a water molecule and see how this would hydrogen bond. I'm going to draw my water molecule in blue. And what you're going to do is just orient the opposite portion. We have the acceptor. We need a donor. So I'm going to orient the donor of a water molecule close to my acceptor on my molecule. So there's hydrogen, there's oxygen, there's hydrogen. Here is water. And here is the donor on the water molecule. And here's the partial negative part on that molecule. So the hydrogen bond is going to be right here in between those two. That is going to be the hydrogen bond. That's where the attraction from the partial positive and the partial negative.
I'm a little confused. I thought oxygen can only have two bonds. So, like, what do we do there? I guess do we just like remove the lone pair?
No. So this is not a true bond, even though we're calling it a hydrogen bond. It's an intermolecular interaction.
Okay, so it's okay. So not what I'm really thinking
Yeah,
of.
so we're not breaking any rules. We're not actually. That's why we usually draw them as dotted lines, because they're not a bond in the sense that those oxygen carbon bonds are.
Okay, gotcha.
But they are an interaction between a partially positive neighboring atom and that partial negative on the oxygen.
Gotcha.
The oxygen still only has two true bonds. Those I'll highlight in green. These are the true bonds on oxygen. The hydrogen bond is not an actual bond form. It's just an intermolecular interaction, which is like a bond, but it's not a real bond form. These molecules could totally float apart, but the carbons and the oxygens here are one molecule. They're not going to float apart. Does that help, Ashlyn?
Yeah, that helped a bunch. Thank you.
Okay, good. All right. So this kind of puts a cap on intermolecular forces, intermolecular interactions. So now we're going to move on and talk about gas laws. The only thing I'll show you is here's just a little bit of a review table down here, just kind of summarizing all that we learned about intermolecular interactions. On your homework, you'll have some questions that'll say, put these molecules or put these substances in increasing boiling point, or order them by decreasing boiling point. And you can do that, even though we did not technically do a practice problem like that, by judging what kind of intermolecular interactions they have. Okay, the stronger the interaction, the higher the boiling point and melting point. The weaker the interaction, the lower the boiling point, melting point. Okay, so you could order things that way. I'm going to skip over this table. We just, for time's sake, it's not really necessary, but it is in your textbook. I think it's a cool figure, just to really look at why the boiling point of water is the highest when you consider other constituents bonded to hydrogen, fluorine, nitrogen, carbon. They're on the same row, but water is unique because of the numbers of donors and acceptors, and that's what that graph is illustrating. But let's move on. We're going to talk about gases so that we can understand gas laws and finish up chapter 8. So gases, we're going to study gases using three properties. Three properties are temperature, pressure, and volume. Temperature, pressure, and volume. Okay. And we're going to see how these three properties are related. And why gases are so unique. They're so much more versatile than solids and liquids. Okay, we can compress them. We can do a lot of different things with gases that we can't do with liquids and solids. So really quick, before we examine some of these pictures I have on the slide, let's define what pressure is. Okay, you guys are familiar with the word pressure. But when it comes to the physical property of pressure, it is a force divided by an area. Okay, a really good example is I have a picture of a tire on here. Think about this tire, all right? What it says here is that the gas inside collides with the walls, and that's what creates pressure. The gas particles hitting the walls. We got a lot of tire in your tire pressure. And that's what keeps a tire aired up, right? For me, it's actually my dad that keeps my tires aired up. Anybody, like when you go like to your parents' house or somebody's house, they're like, your tires look low, we need to check, and I'm like, thank you. I never think about that. So you think about it, thank you. But tire pressure, that's how pressure is created. And the way we have a lot of different units for pressure, by the way. I'm sorry, I don't know why there's so many units, but one of the units right here, we call it pounds per square inch. That's actually how we measure tire pressure. And the pounds is from the force. That's the force on the walls of the tire. Per square inch, okay, a square inch is an area. So pounds per square inch, we abbreviate it PSI, pounds per square inch. So that's one unit for pressure, PSI. Before we move on though, this other picture, what is in this picture? What are these? Anybody know? Helium tanks. That's what a lot of people this morning said. Gas tanks, oxygen tanks. Yeah, we really actually don't know what kind of, I actually can't even tell from the picture what kind of gas is in there, but they're definitely pressurized gas cylinders. How do I know they're pressurized? Well, we have all these gauges up here that is showing the amount of pressure, and very similar to a helium tank. I think I talked about helium tanks before. My daughter, she turned 2 at the end of August, and I wanted to have some helium balloons at her birthday. And it was like so ridiculously expensive to go blow them up at Party Central or whatever. So I just bought a helium tank, and it's still sitting in our bedroom. I don't know what to do with it. I'm like, what do you do? How do you recycle a helium tank? You can't just throw it away, can you? So anyways, we have gas tanks here, and they're highly pressurized. So that's kind of a unique thing with gases, because if I draw a picture of a gas, we know we draw them really spaced out and they're zooming past one another. And because there's so much space, okay, between particles, we can force them together. We can pressurize, we can compress gases, okay? Solids there's no space between solids. We can't pressurize or compress a solid any more than it already is, but we can pressurize or compress a gas. And that's what's here in these gas cylinders. Now, has anybody noticed they're chained to the wall? Why would they be chained to the wall? I mean, think about it. Gas is, all that's in there is air. Okay, so air is not expensive. It's not like these are just valuables we don't want anybody to run off with.
So they don't like fall over and explode?
Yes. One, you don't want them to fall over and explode. Two, if they did explode, I mean, so probably sometimes the pressure up in these things can get up to like 2,000 or higher PSI. If tire pressure is 34 PSI, 2,000 pounds per square inch, that's really, really pressurized. So if one of these were to just go off, it probably could bust through like a concrete wall. And you'll see these often in any research lab or hospital, and they should always be chained up because they could be very dangerous if they were accidentally to get bumped over or something like that. So anyways, all this to say, as we're studying gases, think about the spacing between the molecules and how we can adjust the volume, how we can adjust the pressure and the temperature to learn about gas. Now, this first unit for pressure, as we said, was the PSI, but we're actually going to learn several units. Okay, you ready? Again, I don't know why there's so many. I'm just telling you the news. Okay, the second unit though. I have a picture of the Earth here. And we know there's gravitational force pulling everything downwards. And so I have this column ejecting out of the picture, which is the atmosphere, into the atmosphere. This leads directly into another unit of pressure. Okay, I'm going to read this little paragraph. It says, the air in the atmosphere above you puts pressure on you and you thought it was your chemistry class putting pressure on you. It's not me, okay? Get this, 1 square inch of you has, look at that, 14.7 pounds of pressure. And that, I don't know, that just kind of blows my mind sometimes, at sea level. So we call atmospheric pressure 14.7 psi. I mean, go pick up a 14.7 pound weight. That doesn't feel very light, all right? But I mean, it just feels natural to us. That's just how we live. So, but all that to say is 1 ATM, 1 atmosphere of pressure, okay, because of the actual atmosphere pushing down on us, is equal to 14.7 psi. So that's another unit, and that's how they're related right there. That's kind of, we could use that as a conversion factor, and we will in a little bit if we had to. Another unit of pressure, though, is from this little instrument over here. It's called a barometer. I don't know if you've ever heard of it before. So you've got this Petri dish. Anybody use Petri dishes in your high school biology class? So what you're telling me is that I'm 14.7 pounds lighter. No, I'm just saying if you feel stressed or heavy, it's because the atmosphere, you don't realize how the atmosphere is pushing down on you. All right, back to Petri dishes. So in this Petri dish, we have mercury, okay, mercury in it, and they take the amount of atmospheric pressure, and that is pushing down on the mercury in the dish, and it is forcing the mercury up into this little column that they have inserted to the dish. Now, why am I telling you this? All I'm trying to show you is how they came up with another unit for pressure. They found that 1 ATM of pressure forced that mercury up into the column a height of 760 millimeters. You recognize those units, right? 760 millimeters. So they call this unit, they came up with a unit, they called it millimeters of mercury. The guy who did this, okay, because his last name is Torricelli, they also call this a torr. Just to show you that. But so 760 millimeters of mercury equals, they just plug in a different name for the unit. So same number, 760 torr. All of that is equal to 1 ATM. Now, you're not going to have to really mess around with the unit of torr. It might be on your homework, I'm not sure. If it is, that's how it relates to ATM or anything. Hannah says it's not. But you'll probably for sure have millimeters of mercury and ATM on your homework. Okay, finally, another unit. I told you there was a lot. Another unit is the SI unit. And the reason I'm showing you this one is because remember what the SI units are important for? People do research all over the world, and we're thankful for that. And we have to have a system of international units to communicate measurements and research. And so the SI unit is called the Pascal, abbreviated PA. These are the smallest units, by the way. Pascals are the smallest. So 1 ATM equals 101,325, not 101.325, 101,325. And then if we needed to, we could convert to kPa. In fact, we're going to do a problem later and from a research article that uses kPa. So kPa is just a kilopascal, and 1 kPa is just 1,000 pascals, right? All right, here's everything we just said, summarized in one little statement. So the reason I'm introducing these to you is because there's going to be times when you're doing gas law problems on your homework and on the exam, and you may have to do a quick unit conversion for pressure before you can plug things into a gas law equation. So to actually practice that, let's do this problem. Your tire pressure is 34 psi. What is the number in millimeters of mercury and pascals and in atmospheres? These are all just simple one-step conversions using these relationships on the slide previous. So start with 34 psi. And we're going to cancel out psi, and we're going to convert to millimeters of mercury. So to do that, we need a relationship. How many psi equals how many millimeters of mercury. And the numbers are here, 14.7 and 760. So you just plug those in down here. PSI cancels. Anybody got our answer? Madison said it is 1757.82. And the units there are now millimeters mercury. Okay. Now let's convert it to pascals. So you start with the same number, 34 PSI equals how many pascals? Well, we want to cancel PSI and we want to convert to pascals, okay? That's how the units are going to work, but what's the relationship? 14.7 PSI equals 101,325 pascals. So 34 times 101, you're going to get a really big number here. Times 101,325 divided by 14.7. Oh, my computer has 5% battery. And I don't have my charger. Let me go see if someone has one real quick. 234,357.14. And that is pascals. Y'all start the next one. I need to go grab a charger. It's just plugging over here. I don't. Looks like that. We don't have that plugged. Hold on, guys.
Oh my gosh, I wish I knew.
That's funny. Okay, we're back. Sorry, everyone. Anybody been there? Okay, we're saved. Charging. All right, what'd y'all get for that third one? It should have been 34 PSI times 14.7 PSI to 1 ATM. Good, 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 good. 2.31 ATM. Okay, so the reason I'm just showing you these is because there may be a moment when you do a gas law problem that you just have to do a quick unit conversion. And this was just some good examples. Just a little one-step conversion to get the right units before you plug into the gas laws. Okay. All right, we have arrived to the gas laws. So the first one I wanted to introduce is called the combined gas law. And this just shows us exactly how pressure, volume, and temperature are related. This is actually, just like the name says, it's the combination of three simple gas laws: Boyle's law, Charles' law, and Gay-Lussac's law. You may have heard of those before. So we're going to review those and see how they all come together. And then we're also going to talk about the ideal gas law. Anybody heard of the ideal gas law? PV equals nRT? Maybe? Okay. So that's where we're going today. And that's going to be it for chapter 8. But let's look at this. So it says P1 V1 over T1 equals P2 V2 over T2. What in the world is that? So P stands for pressure. V is our volume, and T is a temperature. And I'm going to make a big point right here. Always make sure your temperature is in kelvins. I noticed tons and tons of problems on the homework that it says it gives you the temperature in Celsius and it asks for the answer in Celsius. If you're doing like here's temperature number 1, find temperature number 2, but always do the problem in Kelvin. Okay, so always convert those temperatures to Celsius, and then in the end, if you have to convert back to Celsius to report your answer, you'll do an extra conversion. But plug in Kelvin temperatures. So this always needs to be in Kelvin. All right, these determine changes in the gas's physical properties. And describe the relationship just like it sounds between pressure, volume, and temperature. And what this is, what the P1, V1, T1, and the subscript of the 2 stands for, the 1 is going to be an initial set of conditions. And the 2 is going to be your final set of conditions. So you'll read problems a lot that say, you have a balloon and initially it has this volume at this temperature and this pressure. Find the volume at this new pressure and the new temperature, okay? And your new temperature and your new pressure would be your P2 and T2, okay? Anything initially that it gives you, you'll plug in on the side of number 1, okay? Anything that changes, you'll plug in on the side number 2. Does that make sense? I hope it does. All right, so essentially, like we said, combined gas law was derived from 3 simple gas laws. So as people started studying gases and how these properties are related, they came up with these laws. So Boyle's law is just relating 2 of the 3 properties, pressure and volume here, pressure and volume. So what we're not relating here is temperature. And what that means is essentially what we're asking is, what does the combined gas law look like when the temperature is held constant? Okay, the reason we're not relating temperature here is because we're not changing temperature. If temperature is held constant, whatever variable is held constant, you can just delete it from the equation. So if we just delete temperature, what are we left with? P1 V1 equals P2 V2. That is Boyle's law. P1 V1 equals P2 V2. So I don't know about you, but I like a good visual. So this visual here is a figure from your textbook. And what we have is a container essentially with a movable lid. You can imagine a handle on it and you can like push it down or pull it up. A good example would be like a bike pump. Okay. Or a pump that you would like air up a basketball or something, or an exercise ball. Anybody ever try to air up one of those big exercise balls with those little hand pumps before? And you're like doing this for like an hour. But a pump is a good example of a container like this. So if we're understanding how pressure and volume are related to each other, essentially this would be our P1. So let's say we have an initial set of conditions. Pressure is 1 atm for this gas. Okay, the gas is inside here. And this volume of our container is 1 liter. That would be V1. If we increase pressure, okay, let's just say we push down on the lid, push down on it, and until we get half the volume, or until we double the pressure. What we're finding, this is P2, this is V2. If we increase pressure to 2 atm, what did we do to volume? Volume decreased by half. Okay, so if we doubled pressure, we decrease volume by half. So how are these 2 related? If we increased 1, if we doubled 1, cut the other in half, they're inversely related. Okay, they are inversely proportional. Okay, as you increase 1, you decrease the other. As you increase 1, you decrease the other. That's how pressure and volume are related. To show that, here's some kind of shorthand ways we show that. We're saying that the pressure, and this right here is the sign for proportional. Proportional to not volume, not volume, but proportional to 1 over volume. And because its pressure is proportional to 1 over volume, that's why we're saying they're inversely related. Okay. Now, what does this mean? PV equals a constant? Well, mathematically, we could plug that in, and we could just plug it into Boyle's law and see if that holds. Let's plug in our P1 and our V1. That would be 1 times 1. That should equal P2 times V2, which is 2 times 0.5. Okay, and if those give you the same number, then that holds, okay? So they both equal 1 on both sides. All right, now the next slide is actually, I think, the coolest one for the day. I told you the whole point with the bonus point opportunity is that I want you to find a way that gas laws relate to health sciences, okay? And they really do. So I literally got on the internet and I just Googled for a little bit to see what I could find. And this is a really cool problem. So this is Boyle's law. So what can happen sometimes, you know, with different medical conditions is, have you ever known somebody or heard of people can have a lung collapse for various reasons? But sometimes it's because you have a cavity space between your lungs that can become filled with air in some way. You can have some sort of air trapped in there, or I'm sure there's many other reasons a lung could collapse. But when you have a cavity of air in there, y'all correct me, you nursing people, if I'm pronouncing this wrong, but I think it's called a pneumothorax. Okay. And so we're going to read about this. So this is literally a problem from this article down here. Okay. 2020. So very recent. And it says, using Boyle's law, P1V1 equals P2V2, we can calculate the change in volume at different altitudes. Okay, so why would that affect anything? Think about what a change in altitude does. We know that pressure on us at sea level is 1 atm. Okay, 1 atmosphere of pressure at sea level. But if you are at the top of Mount Everest, you don't have as much atmosphere pushing down on you. Okay, so at higher elevations, atmospheric pressure drops. All right. Now, why is this important with like this clinical problem or thing we're going to talk about? Sometimes people that are in a lot of danger or their health it's a crisis moment, they have to med flight them or air flight them to a hospital, right? So they'd have to put them in a helicopter and, you know, change altitude for a minute to get to the hospital. So that's exactly what they're talking about here. For example, a patient with a simple pneumothorax being airlifted to their local hospital. If they have a pneumothorax with a volume of 1,500 milliliters at sea level, and here's our pressure at sea level. Looky there, I told you kPa. So what is kPa? That is just the kilopascal. So you could write out 101,325. That would be the number of pascals, okay? But we can use kPa, that's just fine. Okay, so there's our initial set of conditions, by the way. So this is our first volume, that's V1, and here's our first pressure, that's P1. I really love to label these kinds of problems this way. It helps me when I'm going to plug everything in. But then at an altitude of 1 kilometer, which is when we increase altitude 1 kilometer, pressure decreases to 90 kPa. So that's P2. That's the second pressure that we're given. Now, assuming that the patient remains at a constant temperature, let's calculate the new volume of the pneumothorax and see if it increased or decreased. But already, you know, pressure and volume are inversely related. So what's happening to pressure here? Pressure is decreasing because of the change in altitude. So what do you expect to happen to volume?
Increase.
That's right, volume should increase. Now, why would that be dangerous? Why would that matter here? Because it could, if it increases enough, that could totally cause a lung collapse or both lungs to collapse, right? If you have stuff pushing on your lungs. So let's calculate this. We're just going to plug it in. P1 times V1. So P1 is 101.3 kPa. And we're going to multiply that by V1, 1500 milliliters. That is going to equal P2, which is 90 kPa, times V2. So we're looking for V2. So that was P1, V1, P2, and V2. So how do we solve for V2? We're going to divide both sides by the pressure on the second. Divide both sides by P2. So divide by 90 kPa. Now, what's critical here is that your units of pressure are the same. If it had said P2 is X amount of ATM or X amount of millimeters of mercury, you would need to first convert that to kPa, okay, so that it matches the unit on P1. Okay, but they were already in the same units for us, so we didn't have to do any extra conversions. So 90 kPa cancels on this side. Units of kPa are also going to go away on this side because you have it on top and bottom. So you'll do 101.3 times 1500 divided by 90, and V2 equals what?
Wait.
All right, 168.
Yeah, 8.3.
8.3 milliliters. Thank you, Madison. Okay, so our pneumothorax increased in volume, but did it increase to a very, very dangerous level? I was reading a little bit more in this article, and they said a 30% increase could be fatal in some cases. So did it increase 30%? I don't know. How would we find out what percent did it increase? How do we find that out? We know the initial volume is 1,500 milliliters. So initially it was 1,500, and then finally at 1 kilometer elevation or altitude, it is 1,688.3. So it increased. Let's find how much it increased. And we can do that by looking at the difference between those two numbers. The difference between those two numbers is this, right? 188.3 milliliters. That's how much it increased by. And then how do we determine a percent? We would say how much of our original volume is this 188.3. So you do 188.3. Essentially, you would divide that then by 1,500. And then to turn it into percent, you multiply by 100. So you do 188.3 divided by 1,500, times it by 100, and that should give you the percent increase. We found the difference between our initial and final volumes. Okay, Sarah says it was a 12.5% increase. Okay, sounds about right. So it didn't increase to a really dangerous level, but you wouldn't want to go up to like 3 or 4 kilometers altitude. You would want to stay flying around 1 or 2 kilometers to keep that patient safe. All right. So I thought that was a cool example. Next law, though, Charles' law, relates temperature and volume. Okay, so here we're keeping what constant? We're keeping pressure constant. Okay, so what does it look like when we hold pressure constant? We literally delete pressure out of the equation, and we end up with V1 over T1 equals V2 over T2. That's Charles' law. So continuing with our little container visual, if we're keeping pressure constant, then on both sides of this arrow, we have the same pressure, 1 atm. So instead, we're going to change something else. And here, we're going to change temperature. Initially, we have half a liter, so that's V1 of volume in our container. And our initial temperature, T1, is 200 Kelvin, right? So if we heat this up, if we just change one of the variables, let's double the temperature. So T2, so it went from 200 Kelvin, T2 is 400 Kelvin, so we doubled temperature. Well, what happened to volume? To keep the same pressure, we had to double the volume. Volume doubled as well. If we doubled temperature, we doubled volume. So if you increase one variable and the other variable also increases, that means here temperature and volume are proportional. They are directly proportional, not inversely, directly proportional. And we see T and the little proportional sign directly to V. So if you're given an initial volume and temperature, and then we change one of those, and it tells you to find the change in the other variable, you just plug everything into equations like this. Maybe you have 3 of the 4 pieces, and you're looking for the 4th piece, okay? So it's just algebra. You're rearranging to solve for whatever variable you're missing. You're going to practice this a lot on the homework. The biggest thing with these is to make sure your units match on both sides. Again, so like for temperature, you need to have Kelvin on both sides, or for volume, you need to have milliliters or liters on both sides. Okay, make sure they match. Any questions on Charles' law? For time's sake, I'm not going to go into this, but I've always thought hot air balloons are a really cool example of Charles' law. That's how hot air balloons work. If we're increasing the temperature of the gas from that flame inside the hot air balloon, the volume is expanding. We're at constant pressure here. And anyways, the density of the gas changes, and that's why the hot air balloon rises. But if you want to read more about that, I literally pulled that straight from your textbook. So last one, Gay-Lussac's law, relates temperature and pressure. So here we're leaving volume constant. And if we're leaving volume constant, we can delete volume from the equation. What do you get? Can anybody write out Gay-Lussac's law? Just take out volume. So P1 over T1 equals P2 over T2. All right. So here, because volume is fixed volume, we're not changing the lid on our container. We're going to keep it fixed in place. And then we're going to see if we change temperature, what happens to pressure. So initially, we have P1 and T1, 1 atm, T1's 200 Kelvin. If we heat that up, heat the gas up to 400 Kelvin, what happens to the pressure? We see that the pressure doubles as well. If we double temperature, we double pressure. Now, why would that be? If you're heating up gas particles, and this equally applies to Charles' law up here. If we are heating up gas particles, those particles, I know you can't see it, but imagine that there's a bunch of little particles in this container. And if we are heating them up, we're causing them to move faster and faster and faster. They have more energy. And we know when they move, they're bouncing off the walls of the container. And just like with tire pressure, that's what creates pressure, is particles, molecules hitting the walls, creating a force on the walls. That's what creates pressure. So if we're keeping volume constant and we're making those molecules collide with the wall twice as often because they're moving twice as fast because we increased temperature, okay, we doubled it, that's what's causing pressure to double, okay? You can apply these same kinds of thoughts, but just with temperature and volume at a constant pressure to Charles' law. All right, so temperature and pressure are also proportional. T is directly proportional to P. Again, the way I'm going to ask you to do these problems, you'll have 3 of the 4 pieces, and you're solving for, one of the variables. All right, any questions so far on Boyle's, Charles, Gay-Lussac's? All right. One more law, Avogadro's law. This one is actually not in the combined gas law. So this one's kind of a separate law. We're going to relate volume and molar amount. Volume and molar amount. So volume, how much of a gas, how many moles of a gas you have, we find is directly related to the volume of that gas, okay? This is a very silly example, but I think it gets the point across. If I ask you which balloon has more moles of gas, what do y'all think? Yeah, the red balloon. Why? It's bigger, okay? More gas, more moles of gas is directly correlated to a larger volume. Now that seems very obvious to us, but it's actually very much a chemistry relation. So what is Avogadro's law? It says at constant pressure and temperature, the volume of a gas is directly proportional to its molar amount. The more volume you have, the bigger the volume, the more gas must be present. Okay, that's why when you inhale, you're taking gas in, your lungs expand. When you exhale, your lungs collapse. All right, so we're going to abbreviate volume with a V, number of moles with an N. So here is Avogadro's law. V1 over N1 equals V2 over N2. And we're holding pressure. This is only at pressure or constant pressure and temperature. Now, you're going to run into this on some homework problems. STP. What is STP? Stands for standard temperature and pressure. So when we use Avogadro's law, it's much, much easier if we're holding pressure and temperature constant, if we're keeping those constant at the same amounts. Like, to simplify comparisons of gas samples, we need to define a set of conditions, STP. So 0 degrees Celsius, which is 273.15 Kelvin, this is standard temperature. And 1 atm, that is standard pressure. Okay, so if we keep those the exact same, it makes comparisons between volume and moles a lot easier. So if you read a homework problem that says at STP, you have this volume, how many moles of gas are present, you're going to plug in these values for volume and, temperature and pressure. And then what they found, it doesn't matter what gas you're talking about, but at standard temperature and pressure, if you just have 1 mole of any gas, doesn't matter what gas, that gas is going to take up 22.4 liters, okay? We call that a standard molar volume. That's the volume of 1 mole of a gas. Okay, we're almost done, guys. Hang in there. Hang in there. You're doing great. Here's everything we've learned so far. Here's a review of all the gas laws. The combined gas law, Boyle's law, Charles' law, Gay-Lussac's, and Avogadro's law. So if you need a slide on the exam, I say using Avogadro's law, do this, okay? Come to this slide, get that equation. I used to tell people to memorize this, but that's kind of a laughing joke now because you have all your notes and your textbook for the exam. So it's really pointless to tell you to memorize stuff. All right, we're going to talk about the ideal gas law, and then hopefully we have some time to work a few problems. We'll see. Any questions so far on any of that? I know we've talked about a lot of information without working a ton of problems, but all the problems associated with these gas laws so far are going to be very, very similar to this one we worked up here. Okay, you're just plugging the numbers in, solving for the missing variable. All right, let's talk about the ideal gas law. So the relationship between pressure, volume, and temperature, we have a law for that, but if we also want to see how that relates to moles of gas, we have to have another law, because the combined gas law, this one up here, the combined gas law does not have N, doesn't have number of moles of gas. So if we want to see how these properties relate to moles of gas, we have to have a separate law for that, and that is the ideal gas law. In the equation, well, just let me read this first. It says PV and T and N, so we're throwing another variable in. They can be combined into a single equation known as the ideal gas law. And it's this: PV equals nRT. Now your book or on the internet, you might find a different arrangement, and it's the same equation. It's just the variables are moved around a little bit. You might find this: PV over NT equals R. And if you can just see, all they did is they took N and they took T and they divided both sides of the equation by that. But it's the same variable, same relationship. Okay. Now, what is R? Okay, because I don't see that as a variable anywhere up here. And it's not a variable, it's actually just a constant that we plug in so that this equation does make sense. And don't worry about how they came up with the constant or why it's there. But R is a constant. It's the gas law constant. And the value never changes. The units never change. So you can always plug in R. You're never going to solve this equation for R because we already know what R is, okay? R is 0.0821. Liter, look at this. We've got how many units on there? I think this is the most units we put on one particular variable ever. 4 units. Liters. So anytime you're using the ideal gas law, guess what units you have to use on all your different variables? Units that match R. So for volume, anytime you plug in a volume up here, volume has to have units of liters. Why? Because that's the unit in R. Pressure. Anytime you plug in a pressure, guess what units pressure has to have? ATM. Why? Because that's the units on R. Same thing. Moles, this one's really, there's no, you just can't plug in grams for an amount of a gas. You have to plug in moles because, again, that's the unit on R. So this would be for N. So N has units of moles. And Kelvin, we know that's our temperature. So temperature always has to be in Kelvin. So if you go about these problems and you're plugging in a pressure with PSI or millimeters of mercury, you're going to get the wrong number every time. Okay. This is not hard math. Okay. It's some algebra, and algebra can be tough. Okay. I'm not trying to minimize that, but it's not calculus here. I'm just saying you guys can all do this math. I've seen you do it with specific heat equation type stuff. The difficulty that comes with these problems, working ideal gas law or combined gas law problems, is all the freaking units that we have to keep track of, okay? You've got to make sure units match on both sides, and that can just be a headache. So let's work this problem right here. How many moles of air are in the lungs of an average person with a total lung capacity of 3.8 liters? Assume that the person is at 1 atm pressure and has a normal body temperature of 37 degrees Celsius. So how do we solve this? First off, what are we solving for?
Moles.
How many moles? So how many moles? So which variable is that? P, V, N, or T? N. Thank you, chat. So let's rearrange the equation to solve for N. How do we do that? How do we get N by itself?
Divide both sides by RT.
Mm-hmm. See that? Okay. So now we have P times V over R times T equals N. So as long as we have a pressure given to us, volume given to us, and temperature given to us, we already know R, we can solve for N just fine. The only thing we have to check is, do we have the right units on all those variables? Okay, remember, pressure has got to be ATM, volume has to be in liters, temperature has to be in Kelvin, and then we're good to go. So I see that we have liters, there's our volume. See that we have ATM, here's our pressure, but we have Celsius. So Bailey in the chat, yep, says convert to Kelvin. So 37 plus 273.15, because that's how you convert to Kelvin, right? I forgot my units. Okay. So our temperature in Kelvin is 310.15. Now we can plug it all in. So we'll do P times V on top. P times V on top. So that's 1.0 ATM times V, which was, problem says 3.8 liters. Divided by, on the bottom, we're going to plug in R and T. So R is up here, 0.0821. And yes, you have to write in all the units. If I make this a file response question on the exam and you choose to write in no units for R, I will happily mark you wrong. Okay. That's so rude, isn't it? But it's rude to me when you forget your units, all right? Liters times ATM divided by mole times Kelvin. Times our temperature. Don't forget temperature. 310.15. Now, one other key to these. Please take a second when you, because I know a lot of you just want to plug it all into your calculator in one big long problem. And I don't blame you versus doing 4 different calculations. Just plug it all in. Just when, if you do that, put parentheses around your denominator. Because if not, it will divide by R and it will actually multiply by K, or your temperature. But if you put parentheses around that, it will divide by everything that it should divide by. And look, make sure your units work out. Liters on top, liters on bottom, they cancel. ATM on top, ATM. What units are we trying to end up with? We're solving for moles, right? So we better end up with units of moles. Kelvin cancels with the Kelvin from the 0.0821. And we are left with 1 over moles, which is moles. So do 1 times 3.8, divide that by the product of 0.0821 times 310.15. What'd y'all get? Sarah got 0.15. Anybody else get that? Moles? Same. Okay. All right. So 0.15 moles. That's all we really breathe in. Now, an above average person might breathe in more than that, but an average person breathes in 0.15. Well, that's as far as we got this morning. So guess what?